I start with the second follow-up of the problem falling rod on the rough horizontal floor. The second follow-up is mainly to question one sentence in the original problem where it was said that assuming the rod does not slip on the horizontal floor. We'd like to investigate this point, how far this point is correct. If you recall that the rod does not slip on the floor demands that throughout the motion of the rod, that is by the time its angle theta changes from this is the rod. Let's revisit the diagram. This is, we examined it at an angle theta when it has rotated, and in order that it does not slip anywhere during fall, where theta varies from 0 to 90, the normal reaction N must exist, must be greater than 0 at every point. If normal reaction becomes 0 at a point, then obviously it is no longer in contact with the floor and the friction will not come into play. So it must slip at that instant if there is a horizontal force or horizontal acceleration at that instant. We would like to investigate the normal reaction acting on the rod. And to investigate this normal reaction acting on the rod, let us recall the different forces and motion that we had examined so far. We said that the forces it is experiencing are mg, the real forces mg, the normal reaction n, and Fs, the static force of friction. Also, we said that at this instant its angular velocity is theta dot and angular acceleration is theta double dot. We would like to find out n. Our question is how much is n as a function of theta. Now, let us recall that the theta dot we had explained, the angular velocity, we had proved earlier that this is equal to under root 3g by L into 1 minus cos theta. To find out an expression for theta double dot or angular acceleration, we must investigate the equation of rotational motion, that is tau external about the axis of rotation is equal to I about the axis of rotation into the angular acceleration about the axis of rotation. And in our particular problem, we get that torque about the axis of rotation is only produced by mg, and that is equal to mg into L by 2 sine theta. That should be equal to I theta double dot, and I is 1/3 ml square into theta double dot. Therefore, we get from here that theta double dot is equal to 3g by 2L sine theta. And hence the acceleration of center of mass, the tangential acceleration of center of mass at, which is L by 2 theta double dot, and that will be, after putting the value, it will be 3g by 4 into, 3g by 4 into sine theta. This is tangential acceleration, and radial acceleration AR will be theta dot square L by 2, and that gives us the AR is equal to 3g by 2 into 1 minus cos theta. These are the accelerations we need to find the normal reaction. And how do we get the normal reaction? Well, for normal reaction, we analyze the motion in the vertical direction. If I call the horizontal direction as x and vertical direction as y, then we get that equation of motion in the vertical direction is mass into acceleration in y direction is equal to net force in the y direction. That is the basis. Now the acceleration so far we have denoted are at and AR of center of mass. So the AY will be written as m into the y component of the accelerations, and that will be A minus AR cos theta plus or minus also minus just a minute. As I have taken the vertically upward as positive, so AY, according to my definition of the problem, will be equal to minus AR cos theta minus AT sin theta. That is, AY is equal to minus taken common, and putting the value of AR and AT, I get 3g by 2 cos theta into 1 minus cos theta, it is AR cos theta, minus AT sin theta will be 3g by 4 into sin square theta. Putting them in the expression of equation of motion, we get MAY, that is minus 3 mg by 2. If I simplify this, or rather I'll do it afterwards, cos theta into 1 minus cos theta minus 3g by 4 sin square theta is equal to n minus mg. Yes. So the n, that what we were looking for, becomes mg minus, well, there is MAY. So here it will be 3 mg by 4. So mg minus, if I take 3 mg by 4 common amongst both, then I get 2 cos theta into 1 minus cos theta minus sin square theta and this on simplification will give me mg into 1 minus 3 cos theta mg by 4 into 1 minus 3 cos theta whole square. If you simplify this using sin square theta is 1 minus cos square theta and simplifying, you get this final expression of n. Now this is interesting, this final expression of n. This final expression of n, it shows that n becomes 0 at a particular value of theta. And how much is that? N is equal to 0 implies that 1 minus 3 cos theta is equal to 0, or we get cos theta is equal to 1 by 3, whereby we get theta is equal to cos inverse 1 by 3, that means almost 70.53 degree. This is interesting, the value we have got. That means at this angle, the normal reaction vanishes. Now, if the normal reaction vanishes, obviously friction force will also vanish. But the center of mass is accelerating. You can check at this point the center of, or at this value of theta, the center of mass has a horizontal acceleration. And therefore, the rod must slip at this value of theta 70.53. So the question, as it demands, that assuming that the rod does not sleep, that assumption is invalid. It is not possible for the rod not to sleep. The rod must sleep. This is an interesting insight into this problem. The problem does not exist at all because the rod must sleep before striking the floor at this particular value of theta 70.53 degree. Thank you.